Okay, the first part of the circuit is built. This would be the voltage regulator part. This would be the motor output, ground, motor output right here. This transistor here would be this transistor right here, Q7. Q6 is the Darlington pair connected to it at the base. That would be this transistor right here. This one here, this is the series pass transistor. I don't need a tip 41C because it's going to be a small current flowing through there. That would be the series pass transistor for the regulator. Q2, now that's the transistor that modulates or regulates the base voltage of Q1 to allow it to turn on and off accordingly to input. And that's what this is right here. This would be Q2. This one here is the diode connected transistor to act as a Zener diode to give me 8 volts across here. And so now we're going to go ahead and check some voltages here and see how this voltage regulator works now with the test measurements. Okay, so now I've got the power supply hooked up here, and we're going to turn it to 16 volts. So I'm going to turn my power supply up to 16 volts, the bench supply here. And by the way, this is a regulated supply. Get up to 16 volts here now. And now we're going to take our measurements here. The first measurement we're going to take is going to be the measurement across the Zener diode, the transistor Zener diode. We're going to see if we got around 8 volts there with respect to ground. That would be at this point right here. And we're getting about 7.68 volts there. The next voltage would be the base voltage here at 8.7 volts in that range there. That would be the base of that transistor there. That'd be right down here. And we're getting about 8.4. Now the next voltage would be the actual output of the regulator itself, roughly around 9 volts. And let's see what we got here. That would be the regulator output. Would be right here. Would be the regulator output. That's on this side of the resistor, or this on the base collector. That's right here, the red wire right here, and that's the output. And we get about 8.45 volts. And so now we're going to hook up the motor and see if we get close to about 6 volts here. Let's check this voltage here yet at the emitter of Q7. And that would be right here on this side. And we're getting about 8.46 volts. And the reason we're getting that is because we don't have a load on there yet. So we're getting the 8.46 volts because we're reading the voltage across here. There's no drop across here yet because there's no load on here yet. We're going to put the motor on here now and see what our voltages come out to. Okay, now the motor load is hooked up to the circuit. This is the motor output right here. This is the ground. And we're going to check it now at this point right here. We're going to check it across the motor. Okay. And we're getting about 6.94 volts. It's a little bit high, but we're going to be okay with that. And now we're going to start putting a little bit of a load on the motor now and see how the voltage drops. Okay, I'm going to start putting a load on the motor here now and checking the voltage drop. Okay, it drops to about 2.3, 2.4 volts. Okay, that's why we have to build a torque converter now, for this. We have to be able to feed that stall current back over to here to pick the voltage back up again so that we have a more current increase to the motor under those loaded conditions. And that's the next part of the circuit now, is to start building and designing the circuit to receive this feedback now. Now for demonstration purposes, if I were to take a wire from the outside of the motor here, where the motor output is at right here, and I were to take it directly back into the base right here, we're going to see that it's not going to work, and I'll tell you why when we do a demonstration here. So if I hook a wire up from the motor output here now, and I hook that wire to the base of that driver transistor, that feedback transistor, we're going to turn the circuit on here now. And immediately we're up there at 8.43 volts, and that's with the motor, no stall on the motor. So that's why that's not going to work. That's why we have to add circuitry to this. Okay, so now I'll remove that wire back off there again. And now we're back to our normal 6 and 7 volts. as we originally had. Now let's explain why that did that. The target of this design is to feed back motor current back into here to cause that to increase. So we've seen how motor current being fed back in here did increase the voltage all the way out across the motor. It did work. We got a good voltage output. But the only problem is that it was not appropriate for it. It was without any load on the motor, and we don't want that. We want that to run normal until there's a load and then have a feedback. Now here's what happened. This here 24 ohm resistor is a very small resistance here, that pull-up resistance to the base of this transistor here. So there is a impedance mismatch going on here between the output of the motor here and the voltage being built across here being fed back into here. So in order to remedy that, we have to increase the input impedance to this transistor base right here. Now, to increase the input impedance means that we have to, instead of using a passive component, we have to use an active component. And an active component that would increase the input impedance. That means a lower motor current input, as well as some current amplification into here, so as to amplify that change in current here. And that's what I'm going to show next on this design. So then if we take this 24 ohm resistor out of here and we replace it with Q4, an NPN transistor. Now this NPN transistor is in a common emitter mode. The output, well actually it's a input to the base, and it's actually a common collector mode. The input to the base here, and we have an emitter follower here coming up here. The output come off the emitter. So with that being said, then we have a input and impedance increase in here now, because we have a very small current coming out of the base here that would load the motor. All right. At the same time now, we have a current increase because this is a common emitter amplifier, so we have some current gain also. Now here's how I get the values for these resistors here. First, I note that if I'm going to put a transistor as an active pull-up now for this transistor here, I no longer have just a small voltage drop across here as we had before. I now have a 700 millivolt drop yet increase now. So now I have from here another 0.7 volts, so that means now I have to readjust the output voltage here at the regulator itself. And I'm going to adjust that, since this is 8.7, another 0.7 would be 9.4. And by the time I get up through here, it'd be good just to make that about maybe 11 volts. So what I have this design now is at 11 volts here. And that means in order to get that 11 volts, I have to change R1 now. And then I go through the same process I did before through Ohm's law to come out with a resistance of 180 ohms for R1. And that will increase the output voltage 11 volts. And that will accommodate for the voltage increase necessary to run Q4. Okay, so I took the 240 ohm resistor out. I now have the 180 ohm resistor in here now. And so now we need to start working on the biasing for Q4. Here's how I get the biasing for that now. Now I know that from previous that I have here 12.5 milliamps flowing through this voltage divider to bias Q2 on. And that gives a proper bias for Q2. So I need to keep a hold of that 12.5 milliamps and have that flow through Q4 now. Alright, so in order to get that there, I'm going to assume a beta of 50 for my transistors here. So by assuming a beta of 50, I come out with the base current, and then I take 10 times that base current. So when I come through that calculations, I end up with about 1/5 of the divider current. So our divider current was 12.5 milliamps. I take 1/5 of that, and that gives me about 2.5 milliamps. And that's how I come up with my calculations for divider currents for these transistor stages that's being added on now. Okay, again, now to solve the resistor values here, it's just a matter of taking our voltage here, our 8 volts, 0.7 volt base emitter here, and an additional 0.7 volts base emitter, which gives us 8 plus 8, 8.7, all the way up to 9.4 volts. We now have 9.4 volts sitting at the base of Q4. We take that voltage and we divide that by our 2.5 milliamps, and that will give us our pull down resistance of 3.6K in that range. And then we take the output voltage from the regulator of 11 volts, and we subtract 9.4 from that, and that gives the voltage drop across R3, and then we divide that voltage drop by 2.5 milliamps, and that gives us around 620 ohms. So now we're going to go ahead and build this circuit and see how close we get to our calculated values here. Okay, here's that R2X right here, 24 ohms right here. We're going to take that out, and then we're going to replace that now with the transistor Q4 and its bias circuitry. Okay, our Q4 here, the emitter couples into the base. That's the emitter right here, and that couples that yellow wire into the base of the transistor here. Here's the base pull-up resistor connected to its collector, connected to the output of the emitter of the voltage regulator output, and that's what we have going on here. 620 ohms to the regular output, and the collector goes to the same place, and the collector and the base connected there, and we have our pull-down resistor of 3.6K to ground. Okay, now we're going to turn it on and see what our measurements come out to. Go ahead and hook this up now. I can hear the motor running. We're going to take a voltage measurement now at the output here of the voltage regulator, and that will be right here. And we're at about 10.64, and we're shooting for about 11 volts, so we're pretty close there. Now we're going to take a voltage measurement at the emitter here. And that's about 10.65 volts. Now we're looking for about 9.8 volts. Let's take a voltage measurement across the motor now. We're at 9 volts. Alright, here's why. Because we increased the output voltage here, and we did all this, we have our 11 volts, pretty close to 11 volts. We have proper output here, but we need to increase this resistance here, the series resistance here. Before we had 33 ohms. Now we have to increase that to around 100 ohms. The way I got that resistance value was to solve for taking the output voltage here, 11 volts, subtracting two base emitter voltages here, Q6 and Q7, to get into about 9.8 volts, and then putting the 6 volts across the battery or across the motor, subtract the difference between the two, and that gives me the voltage drop across this resistor here. And then for current, right now I'm using 50 milliamps to run the motor at this point at normal running conditions. So I divide 50 milliamps into that voltage across here, and that gives me around 100 ohms for the series resistance. So now we'll put that in there, and we'll see how much that drops the voltage and gets closer to 6 volts now. I'll remove the 33 ohm resistor, and in place of that I'll put the 100 ohm resistor in there. There's a 100 ohm resistor. We'll put power to the circuit now. The motor sounds a little slower now. We're going to turn on and check our voltages now. Again, we'll check our output voltage here, which would be the regular voltage. Then we'll check across the motor. Our regular voltage, about 10.64. Looking for about 11. And here's the voltage across the motor now. And there's our 6 volts across the motor. So we're good on the motor voltage now. We are exactly where we wanted at. So now comes the next part of the design. Okay, now that was circuit change number 1. We are one step closer now to getting our motor current signal back to here to increase motor current. Alright, now what we have accomplished here so far is we have increased the input impedance to the driving transistor here, the sensing transistor here, that's going to cause the output voltage to rise under signal conditions. We've increased the input impedance by putting a transistor in here in a common emitter configuration. That increases automatically the input impedance, as well as gives us some current amplification into here. So now we have that accomplished, but now remember, our signal voltage coming off the motor is a negative going signal. When the motor begins to stall, we have a negative signal coming through here. And this is an NPN transistor, so we now have to invert that signal so that we can feed that into here. So that brings us to circuit change number 2 now. Circuit change number 2 requires us to now place at the pull-down resistor of Q4. our pull down resistor right here of 3.6k ohms of Q4, we can now replace that with an active pull down, and that would be transistor Q5, a PNP transistor. With a PNP transistor, we can now receive a negative going signal into the base, and it will invert that signal. It will actually take that signal, amplify that signal, and give us a negative going signal to the base of Q4. And by going into Q4, we then can turn Q4 off, which eventually turns Q2 off, and then Q1 increases in voltage. The only way that we can increase current and voltage power output to the motor is if Q2 begins to shut down. That's how we get our increase. So that's why I said by taking motor current into the base of this here would have done that initially, but because of the impedance mismatch between the motor and the Q2 base, we have to add all of this circuitry to make it compatible so that we can make the motor current compatible to the base current here to cause our increase in current output from here. So now by taking a PNP transistor and putting that in place of the R4X here, which is the pull down resistor for Q4, we can now again have a higher input impedance coming in. That means smaller yet motor current signal now, as well as some more current amplification, which means is now that the current signal coming in, being very small, can actually be amplified. So the smallest change in motor current will affect a very large change on the output of this, causing this to increase greater. Okay, now how do I get these values here? Again, I take my divider current that was flowing through here of 12.5 milliamps. That's a divider current initially. That divider current, I divide that by 5 again. That means taking a beta of 50 for the base current, and then take 10 times that for the divider. Gives me 1/5 of divider current originally to the collector here, and that gives me about 500 microamps. And so again, we just solve for our voltages. What we have here, we start here at 8 volts and follow this loop, 8.7, 9.4. Now we come back this way here, and now we're going to subtract 0.7 volts because we have a PNP transistor. So we subtract 0.7 volts, and that brings us back to 8.7 volts now at the base here. So now from ground to the base is 8.7 volts. We divide that by our 500 microamps for this divider current now, and that gives me about 18k ohms for R4, which is the base. Now this would be the base pull down resistor for the PNP transistor. The pull up resistor would be take this 8.7 volts and subtract that from the output voltage here of 11 volts. That gives the voltage drop across R5, and then divide that voltage drop by the 500 microamps, and that will give us 4.7k ohms in that area there. And that will be our divider current that will bias Q5 on into its linear region. And when that's biased in that linear region, the current flowing through here would be the same current that's flowing through here originally for Q4 to be the bias current to put Q4 in a linear region. And with Q4 being linear, it also allows the current to flow through here to keep Q2 linear. So everything is now, all these pull-up resistors and pull-down resistors that we originally had in the circuit are now changed to active resistance changes now using transistors, so that we can accomplish signal feedback and things. Okay, so let's go ahead and build this now and take some measurements again. We'll build this part, and then we'll take some measurements here again and make sure that we're getting our 11 volts here, and make sure we're getting our 6 volts across the motor, and that will ensure then that we have proper currents flowing here to keep everything the same.